Hello everyone and welcome back. So in this video we're going to move on to calculate normals, and it looks like we've moved on to Maya 2011 for some demonstration first.
No, actually, I just gave up on coding. I'm becoming a modeler, so I'm just demonstrating my awesome modeling skills
I
right now.
see that. Wow.
We are going to hand manipulate every triangle for our terrain for the entire world directly in Maya.
Well, the size just dropped considerably.
Yep, that's it. This is our entire world right there. So now the real reason we're here is to discuss the new way that we're going to be addressing normals. When we had the hexagon type grid, we'd come up with a fairly efficient way of creating normals that looked decent. They weren't perfect, but they looked okay. What I found with the calculation of the normals with this type of grid, that trying to oversimplify the calculation just yielded in some really, really bad looking normals to the point where it just wasn't acceptable anymore. Because what I was getting were these little diamond patterns of shading inside of the terrain, and it was just horrendous. So, I started thinking about it and realized that, this stuff is going to be all baked out anyways. So it's pretty much you calculate it once, and unless you're sculpting and modifying it, it never gets recalculated. But even if you're sculpting and modifying the terrain, those normals can be recalculated at a single time and saved out prior to the baking out process. So it's not going to be so bad to do a true calculation of normals. Now, the normals that we're trying to calculate are vertex normals as opposed to face normals. Now, what's the difference between the two? That is why we've got Maya, because it's a lot easier to demonstrate this inside of Maya than it would be for me to try to draw this in Photoshop. So what I've done is I've done a mock-up of a single square of our terrain with all 8 of its triangles and all 9 of its vertices. If I were to go ahead and let's just display for the moment, we'll do vertex normals. This is what we want to get, sort of. Now, right now, we see that each vertex has multiple normals. All the ones along the edge have 2 normals, except for this big mess in the center, which has, looks like 8 normals. So 1, 2, 3, 4, 5, 6, 7, 8. So 1 for every line leading into this normal. Now, if I turn or click off, we can see that this patch looks very faceted. That's because I have hard edges on it, which is why we're seeing all these different normals. So technically, when we're to export this, each one of these vertices would be 2 vertices, except for this one, which would be 8 vertices. That's how we get edges inside of an object. What we would prefer to see is by selecting this object, if I take normals and I soften the edges, in other words, I'm getting rid of all the edges, turning this into a single patch, we get smooth shading across. And you can see that we now have 1 normal at each one of these vertices. This is what we want to end up with at the end of the day. The trick is how do we get this? What we do know is that we have the height information and the position information for each one of these points. But how do we calculate this normal based off of the information? The way we're going to approach it is by getting the normals of each of the faces that surround a particular normal and averaging them together. So what we're going to try to accomplish is to, let's see, if I go to display polygons and I turn on face normals, and for the moment I'm going to turn off our vertex normals. What we're going to do is we're going to calculate the face normals for each one of these triangles, and then we're going to take these face normals and average them together to get the vertex normal in the center. So that's what we're going to go to, but now the problem becomes, how do we get a face normal when all we have are 3 points? Well, if we take those 3 points and we determine two of the edges. I only need two edges. And I use a cross product of those two edges, I can determine the normal of the face that is made up by those two edges. So that's how we're going to do it. Basically, we're going to write a method that is going to take each of the points surrounding a vertex, calculate out two of the normals for each of the triangles, do a cross product of that, normalize that cross product so each one of these normals is a unit normal, and then I'm going to take all of those, add them together, and then divide them by 8. That result is going to be the normal of the vertex in the center. So that's what we're going to do. So hopefully that visual demonstration made all the code we're about to write a little bit easier to understand. So let me go ahead and minimize this and jump over to code. And to start with, I'm going to go ahead and close down everything. Jump over into vertex cache, close everything over here. And let's see, below get height, let's go ahead and make a public static calculate normal. Well, void calculate normal. We're not going to return any information from it, but we're going to calculate the normal for a position that we are given, and then we'll update the vertex at that position, or the normal of that vertex inside of the dictionary. That's why we're not going to return anything. So this will be normal. Takes in a vector2 position.
Check your spelling on normal.
Yeah, that's close. Wait, you don't like my spelling?
Just giving you a hand.
All right. First check. Does this... Well, hold on. I hit caps lock again. All right. First thing we want to do. Does this vertice actually exist? So do a check on contains key, position. If it does not exist, return. We're not going to do anything else. Then we'll set up another variable. We'll call this n. And for now, I'm going to set this to a vector3 dot up. Semicolon probably help. This is just because I'm going to wrap everything else up in a try catch, but I still want to be able to return something out. So if all else fails and we get a failed calculation, I'm still going to return a vector that is purely up so it doesn't show up as black. So we'll do a try, and I'll deal with the catch first. And it's just going to be a simple debug.log. And I'll do a log error on this one. So it says error, can't spell error either, error at. And then I'll pass in the position. This will just let us know that there was a problem at that particular position. And then we will set the very end our vertices, position, and we'll set its normal equal to n. All right, now for all the fun calculation stuff. We're going to need a whole bunch of temporary variables to do this. So we're going to start off with P0, which is going to be the point in the very center. So this will be equal to vertices. And I'm going to do a new, well, in this case, I just need to pass in position. Yeah, I do need to do the full thing. So it's going to be new vector2. And this will be, what am I thinking here? No, I don't need to do this. I've lost my mind. No, we're just going to pass in position, and then we'll get the full 3D position from this point. Because we need to accurately calculate our edges, otherwise we're going to get bogus information from our normal calculations. So this is our center point. Var P1 equals, again, vertices. This time we'll use a new vector2. This will be our position dot x minus spacing by position dot y plus spacing. So this is going to get our point that is up and to the left of our center point. And then I'm going to get its position. Now, this same thing is done for the next 7. So that's 2, 3, 4, 5, 6, 7. So P2, P3, P4, P5, P6, P7. Apparently, I can't count right either. So P8. So then we will use position X, and that will be plus spacing. This will be plus spacing. So I'm getting the positions of all the vertices along the top row. Then I will get the spacings along the center row. So these will be position Y for both. And then for the bottom row. Alright, so that will give me those. So that's just getting our sample points. Now we need to calculate the normals for each of those triangles, and there are 8 of those. So this will be n1 equals a vector 3 cross product. Now, the cross product is going to need 2 edges or 2 vectors to pull this off. So we're going to get our first vector by taking our P1 and subtracting P0 from it. Our second edge will be P2 minus P0, and I will take those and normalize it. Same thing gets done for the other 7 triangles. So the 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, and 8. All right. Second triangle is going to start at P2 and go to P3. Basically, all I'm doing is, if we look at Maya, and let's say, trying to think the best way to arrange this. So if we're looking down on it, and we say that this is P0, and this is P1, P2, P3, P4, P5, P6, P7, and P8. Basically, I'm calculating this edge by going P1 minus P0, getting this edge by going P2 minus P0, taking the cross product of these 2 edges, which yields this face normal. Then I'm going to take P2 minus P0, P3 minus P0, and I'm just going to work my way around in a clockwise fashion. And then at the end of it, I'll have all of the normals for each of the faces.
Now, was I crazy a second ago when you said P1, P2, P3, then P4, you went over to the left-hand side, center, edge? It didn't look like you went clockwise. That's unless I'm just...
Actually, I do zigzag back and forth when I'm looking at it. But this does go to P4.
Okay.
But what ends up happening is when I do the calculation, I'll do P4 and P0. I'm just looking at my numbers right now and how I ordered it. Because I was doing it originally once, and I started swapping them around when I had problems with it.
Okay.
So P4, but P4, P0, and then P1, P0. So it will be there.
Okay.
But it goes. So basically, I'm going to do this triangle, then this triangle, then I do this triangle, and then I do this triangle, followed by this one, this one, this one, and this one. Okay, so basically I'm doing it in rows.
Okay.
But I can change it.
No, it's all good. It's all good. I just wanted to clarify when at the very end there you said you're just going to work your way clockwise all the way around.
I'm starting in the middle, then out. So in, out, and then here is P6. So here, then I do this one. Wow. So I do it one way here and do it a different way there.
Yep. That's okay,
Just hold
though.
on. Just hold on. Well, in the end, I
It's
have
all
all
good.
8 of them
Yes,
calculated.
that's
So
right.
that's what matters.
That's right.
I remember I had to swap them around because I had reversed. If you reverse these normals or the order of these edges and the way you're calculating them and the subtractions, basically all you do is you end up calculating your normal upside down. So your normal is facing down instead of up,
Mm-hmm.
and you end up with black. So if you mess this up and you see black, you probably just reverse the normal somewhere.
Reverse the vector, an edge.
Well,
Which is
you
which
reverse an
causes
edge to cause a reverse.
exactly.
Normal.
Mm-hmm.
So then let's see. This is P3 followed by P5, and this would be P6 followed by P4, and then P5 followed by P8, and then P7 by P6, and then P8 by P7. All right. So hopefully, if I didn't make any typos, that should work right. If not, we'll get some funky results. So n equals n1 plus n2 plus n3 plus n4 plus n5 plus n6 plus n7 plus, you guessed it, n8. Then we divide that by 8f. That gives us our final normal back out. So that should give us the correct normal calculation. Unfortunately, we can't tell whether or not that's going to work for us not until we finish putting the terrain patch together. And we can't finish putting the terrain patch together until we finish the rest of all these methods in the vertex cache. So we're going to have to pretty much wrap up on this video, hoping that we got it right. Implement tangents, a few more methods over the next couple of videos, but we will get to the train patch once the vertex cache is done, and then we'll be able to test all these and fix anything if it happens to be broken.
Okay, fantastic. So I'll scroll down real quick.
Or I could just do that too.
Yeah, that's good. Okay. Okay, good deal. I didn't see line 194. I had forgotten you'd put that line in there.
Oh yeah, where I actually assigned it.
Right. I was just going to say, wait a minute, are we going to assign it at some point? But yeah, I see it at 194. Fantastic. All right, well, with that, ladies and gentlemen, that's going to wrap up this video, and we will see you guys in the next, where we will be calculating tangents. Thanks a lot.